You can buy commercial stamps, but the selection is somewhat limited. I think it's a good idea to know how to make your own. I'm going to make a stamp that will create this arrow image. The starting point is a piece of tool steel. First I'll file the top end or striking end of the tool, like this. Next I'll thin the bottom end, the part where the image will be. It's important that this is smooth and exactly perpendicular to the shank. I'll test it by making it stand up. After refining with sandpaper, I'll touch it with a bit of dye and then draw the image on. The shape is then achieved through the use of a saw and files. I'll use a lump of clay to check the tool. It's worth taking time to make sure you get the image just right, because when properly heat treated, this tool is going to last for generations. In order to convert this soft steel into hardened steel, we use a specific heat treatment called hardening and tempering. The two words refer to two steps of an operation and really should be used both together, but sometimes for shortcuts we talk about hardening or tempering. In fact, you never do one without the other. The first step, hardening, involves heating the steel until it goes through a critical change. Its crystalline structure will convert from one shape to another shape. The new shape is much tougher than the first. In order to freeze the action at that point, we need to have a controlled cool down or quenching. If it cools too rapidly, there are stresses developed which will cause the tool to crack. If it cools too slowly, it will convert from one phase back to its other, from the hard back to the soft. So we need to find some material that will draw the heat away pretty fast but not too fast. And the material we use for that is oil. This steel is called an oil hardening steel. It's been formulated specifically to work with quenching oil. Now commercially they get very complicated about this, using oils of specific viscosity heated up to a specific temperature. In our case, we don't need to be quite that critical. I'm using motor oil at room temperature. I'll be hardening just the bottom inch or so of the tool. My indicator is color. I'll be heating until it's a bright, luminous red. Another indicator, if you're not confident about reading color, is the fact that the steel, when it reaches critical change, when it goes through that phase change, loses its magnetism. So you can keep a magnet close at hand and just touch the tool to it. And if it does not pick up the magnet, you'll know it's at the right temperature. That's approaching the right color. And now I'm going to very quickly move over to the oil and stir with the tool. The stirring is important. If I plunge the tool in without stirring, it's immediately surrounded by an envelope of hot oil, and that defeats the purpose. By stirring, I'm constantly bringing it into contact with fresh, cool oil. I'll keep it there until it has cooled sufficiently to hold. Clean it off and then check it. At this point, the steel should be very hard. It's also brittle. But let's deal with the hardness first. I'll rub a file against it. This is the same file that a minute ago was used to shape the tool. Now the file will not cut in. There's a high-pitched, glassy sound. Compare that sound with that. This is the back end. It's not been hardened. Tool end. You can hear the difference. If it did not have that sound, I'd repeat the process I just went through. Something to be careful about is heating it to the right color, but then taking too long to get it over to the oil. As I said, at this point the steel is very hard but brittle. So brittle that if I was to strike it, chances are it would shatter. This would be disappointing since I just spent so long making the tool. It would also be dangerous. In order to relieve that brittleness, I'll go through a second heat treating operation called tempering. The tempering operates at about 1/3 the temperatures that we just saw. In order to read the correct temperatures, I need to clear the metal. It has a gray scale, and I'm going to get rid of that with sandpaper. The hardening process that went to bright red operates at about, well, a little over 2,000 degrees Fahrenheit. The tempering that we're about to go into operates between 400 and 600 degrees. For that reason, you'll want to use a small torch, a gentle flame, and go slow. I think if there's a single common problem, it's in running right through this process and missing it because it happens like that. Last time I moved the flame around. This time I'm going to keep it constant, about 1.25 inches, 1.5 inches away from the tip. Nothing's going to happen for a few seconds, and then you're going to see a rainbow of color. There it is. You'll see blue in the center. Next to it is plum, followed by brown, followed by a straw or bronzy yellow. It's that bronzy yellow that I'm going to watch. As I keep the torch here, that color is going to crawl toward the tip. It's also crawling up the handle, but I'm not too worried about that. I'm watching the one that's going toward the tip. And when the straw gets to the tip, then again, moving quickly, I'll quench the tool. Now, the yellow itself doesn't mean anything. It's the fact that it indicates a certain temperature. At that temperature, there are changes going on inside the steel that relieve the brittleness without sacrificing hardness. If I were to wait too long, or the longer I wait, the more sacrifice there is. That is, the greater flexibility, but the less hardness. And there you can see we've got yellow on the tip, which is maximum hardness, but enough flexibility to make an impact tool like this. Behind that is brown, then plum, then blue. If I had continued heating a little bit further, those colors would have advanced to the tip. The plum and the blue have the most flexibility, but at the greatest expense in hardness. The most common chemical for darkening sterling involves the use of a chemical called liver of sulfur, or hydrosulfurated potash. This is familiar to most jewelers as that rotten egg-smelling stuff. It's usually sold as a gravel. You mix it up with water. A little goes a long way. The size of a pea is right for, say, a cup of water. I like to use warm water because it dissolves faster. If you drop a piece of sterling into that mix and leave it for 2, 3, 4 minutes, it will turn black, or at least a dark gray. But you should know that there are a number of beautiful colors that come along the way. Let me demonstrate those. The first color is a golden or bronzy color. It's a little darker, just showing brown, for instance, in that corner. And next, we'll start to see a vermilion, a bright red. We're just getting a hint of that in the center. These colors are a result of temperature of the liquid, cleanliness of the metal, and the amount of time that the liver of sulfur is allowed to remain on the metal. Just beginning to see the color patterns developing up here in the corner.